Welcome back. Before we start our deep dive into today's topic, please take a second to hit that like button, subscribe to the channel, and turn on notifications so you never miss a technical breakdown. It really helps the channel grow. Apache Torque is an open-source ORM framework originally developed by the Apache Software Foundation. Unlike modern frameworks like Hibernate, Torque uses XML to define database schemas and generates corresponding Java code. This approach gives developers full control over SQL generation and is particularly useful in legacy environments where precise query tuning is essential. Torque shines in scenarios where developers require total control over SQL generation. It's perfect for integrating with legacy databases that don't conform to modern standards. Its lightweight nature makes it suitable for performance-critical applications, and its customizable code generation pipeline allows for tailored output based on project needs. The architecture of Apache Torque revolves around three main components: the schema definition in XML, the code generation engine powered by Maven, and the runtime layer that executes database operations using JDBC. This modular design ensures flexibility and vendor independence, making Torque adaptable across different database platforms. In Torque, the schema is defined using XML, which describes all tables, columns, primary keys, foreign keys, and relationships. This schema serves as the blueprint for generating both Java classes and SQL scripts. It also supports advanced features like inheritance and custom data types, allowing for sophisticated modeling of real-world data structures. Torque's code generation process is handled by a Maven plugin that reads the XML schema and produces Java classes. These include base classes for each table and peer classes that provide static access to database operations. Templates can be customized to fit specific project requirements, and regeneration won't overwrite manually written business logic. At runtime, Torque communicates with the database through standard JDBC APIs. It supports connection pooling for efficient resource usage and integrates with transaction managers for ACID compliance. Developers can also hook into the query execution lifecycle to optimize performance or add custom behavior. One of Torque's strengths is its ability to work with a wide range of databases, including MySQL, PostgreSQL, Oracle, and SQL Server. It uses customizable SQL dialects to ensure that generated queries conform to each database's syntax and features. This makes Torque a versatile choice for multi-vendor environments. Torque's minimalist design results in low memory and CPU overhead, making it ideal for high-throughput applications. It excels in batch processing scenarios where performance is critical. Additionally, developers can bypass the ORM layer and execute raw SQL for maximum efficiency when required. Torque provides a criteria API that allows developers to build dynamic and type-safe queries programmatically. It supports complex operations like joins, subqueries, and aggregations. For cases where the criteria API isn't sufficient, Torque also allows direct execution of raw SQL, giving developers ultimate flexibility. While Torque supports common relationship types like one-to-many and many-to-many, it doesn't automatically manage relationships like modern ORMs do. Instead, developers must manually define and handle relationships, which provides more control but requires additional effort. Lazy and eager loading strategies can be implemented explicitly. Torque integrates seamlessly with Java Transaction API, JTA, and Spring Framework for robust transaction management. It supports nested transactions and ensures ACID compliance. Developers can also manually control rollback behavior, giving them fine-grained control over transactional logic. Unlike some ORMs, Torque doesn't include built-in caching. However, it can easily integrate with external caching solutions like EHCache or Redis. This allows developers to implement caching strategies tailored to their application's needs, especially beneficial for read-heavy workloads. Security in Torque relies heavily on proper implementation practices. The Criteria API helps prevent SQL injection by parameterizing queries. However, input validation must be handled manually. Connection pooling adds an extra layer of security, while authentication is typically managed by external frameworks or middleware. Torque is especially useful for brownfield projects where legacy databases need to be integrated into modern Java applications. Its schema reverse engineering capabilities allow quick adoption, and it can coexist with existing ORM tools. This makes it a viable option for gradual migration strategies. Configuration in Torque is managed through XML files that define database connections, schema locations, and code generation settings. These configurations can be tailored for different environments using Maven profiles. Torque also validates configurations at build time, reducing runtime errors. Debugging in Torque is facilitated by detailed logging of generated SQL queries and comprehensive exception stack traces. Developers can implement custom exception handlers and use profiling tools to identify performance bottlenecks. This level of visibility is crucial for maintaining large-scale applications. Testing Torque-based applications involves both unit and integration testing strategies. Unit tests can use mock databases, while integration tests run against real databases. In-memory databases like H2 are commonly used for fast test execution, and tools exist to generate test data automatically. When comparing Torque to Hibernate, the key difference lies in control versus convenience. Torque provides more granular control over SQL generation and schema management, while Hibernate abstracts much of this complexity. Hibernate benefits from a larger community and automatic relationship handling, but Torque excels in performance-critical and legacy scenarios. MyBatis and Torque both offer fine-grained control over SQL, but they differ in approach. MyBatis maps SQL queries to Java methods using annotations or XML, while Torque generates Java classes directly from the schema. MyBatis is more flexible in mapping arbitrary queries, whereas Torque enforces consistency through its generation pipeline. To get the most out of Torque, it's essential to follow best practices. Keep your XML schema under version control to track changes. Use peer classes for static access to database operations. Avoid over-customizing templates to maintain upgrade compatibility. And always profile your queries to ensure optimal performance. Common pitfalls when using Torque include errors in manual relationship handling, over-reliance on raw SQL that bypasses ORM benefits, ignoring transaction boundaries leading to data inconsistencies, and neglecting build time validation, which can cause runtime failures. Torque supports inheritance mapping using a table-per-class hierarchy strategy. This allows shared logic to be defined in a base class while generating appropriate SQL for each subclass. It's a powerful feature that reduces code duplication and promotes maintainability in object-oriented designs. Custom types in Torque allow developers to define how Java objects map to SQL columns. This is particularly useful for complex data types like enums, JSON, or custom objects. Once defined, these mappings can be reused across multiple columns, enhancing type safety and reducing boilerplate code. Torque allows execution of stored procedures through peer classes, supporting in, out, and in-out parameters. This integration works seamlessly with Torque's transaction management system, making it ideal for encapsulating complex database logic within the database layer itself. Torque's multi-database support allows a single schema to target multiple database vendors. By defining custom SQL dialects, developers can ensure query compatibility across platforms. This feature simplifies vendor migration and enables applications to run in diverse database environments. In batch processing systems, Torque's lightweight design and ability to generate optimized SQL make it an excellent choice. It minimizes ORM overhead, allows custom SQL for performance tuning, and integrates well with scheduling frameworks like Quartz for automated execution. When modernizing legacy systems, Torque's schema reverse engineering capabilities allow quick adoption. It supports a gradual migration path, integrates with existing tools, and maintains backward compatibility, making it ideal for enterprises transitioning to modern architectures. Enterprise reporting systems often require complex joins and aggregations that Torque handles efficiently. Its support for raw SQL enables advanced queries, and it integrates well with BI tools. Performance tuning capabilities make it suitable for large datasets commonly found in enterprise environments. Benchmarking Torque against other ORMs reveals its strengths in performance and memory usage. It typically outperforms heavier frameworks in query execution time and scales better under load. These metrics make it a strong candidate for high-throughput applications. While Apache Torque is not under active development, it still maintains a community through mailing lists and forums. Documentation is available on the Apache website, and third-party tutorials can help bridge knowledge gaps. However, commercial support options are limited compared to mainstream frameworks. Apache Torque is currently in maintenance mode, with no major updates planned. However, it remains a viable option for specific use cases, particularly in legacy environments. For new projects, migration to modern ORMs is generally recommended, but Torque's legacy support capabilities ensure its continued relevance. To get started with Apache Torque, the official Apache documentation is your best resource. Community forums and mailing lists offer additional support, while third-party blogs and tutorials provide practical insights. Sample projects on GitHub can serve as excellent learning tools for hands-on experience. Setting up Apache Torque involves configuring Maven dependencies, defining your XML schema, running the code generation plugin, and setting up database connections. This process ensures that your application is ready to leverage Torque's ORM capabilities from the ground up. Let's walk through a simple project using Apache Torque. First, define your schema in XML. Then, generate Java classes using the Maven plugin. Next, write business logic using peer classes to interact with the database. Finally, execute queries and handle the results in your application. When troubleshooting Torque applications, start by checking your XML schema for errors. Validate database connection settings and review generated SQL for correctness. Enable detailed logging to trace issues and consult community forums if problems persist. In summary, Apache Torque provides unparalleled control over ORM operations, making it ideal for legacy systems and performance-critical applications. While it requires more manual effort than modern frameworks, its relevance in enterprise environments remains strong. Understanding its architecture and capabilities can give you a competitive edge in specialized scenarios. Thanks for joining me on this deep dive into Apache Torque. If you found this tutorial helpful, please give it a like and subscribe for more technical deep dives. Drop your questions or share your experiences with Torque in the comments below. I'd love to hear from you. And that wraps up our explanation. If you found this useful, please hit the like button and share it with a fellow developer. Don't forget to subscribe for more technical tutorials. Thanks for watching, and I'll see you in the next one.